I want you to picture a scenario. You are flying a long-range route, high latitude, somewhere over the Canadian archipelago.
Yeah.
You are tired, the cockpit is dark, and you are staring at your instrument.
Yep, been there.
You check your position, you're at 75 degrees north, you look at your compass, it's sluggish, it's dipping, it's giving you a reading, but you have this nagging feeling that if you follow it, you are going to end up hundreds of miles off course, potentially running out of fuel over the Arctic Ocean.
A very real possibility.
The fundamental challenge here isn't just flying the plane, it's navigating across a spinning sphere filled with molten metal that is constantly trying to lie to you.
That is a terrifying scenario, but it is exactly, and I mean exactly, why the ATPL syllabus goes so hard on Earth magnetism. It's not just about knowing which way is north.
Yeah.
It's about understanding the specific physics, the errors, the geometry, and the calculations required to interpret what that compass is actually telling you. Because at 75 north, north is a very relative term.
It really is. And that is our mission today. We are doing a deep dive into Earth magnetism. But we aren't just reading the textbook definition. We're going to deconstruct the physics, break down the errors, especially those turning and acceleration errors that everyone trips up on.
Oh, absolutely. The classics.
And we are going to master the mental math. If you are prepping for your ATPL theory exams, this is the deep dive you need.
Precisely. We need to move beyond the basic red end points north understanding. The examiners want you to understand the mechanism. Why does the needle dip? Why does the variation change over time? And most importantly, when you are under the pressure of the exam clock, how do you calculate the true heading from the compass setting without getting the sign wrong?
I'm ready to get into the weeds on this, and I don't want to just nod along today.
Yeah.
I've been looking at these question banks, and some of this stuff feels, well, it feels counterintuitive. I want to challenge the why behind these rules.
Please do. The why is what makes it stick. It truly is. If you just memorize the mnemonic, you might flip it when you're stressed. If you understand the geometry, you can derive the answer even if you blank out.
Let's start with the source of the problem then. We're navigating on a planet that's essentially a giant wobbly generator. We have to distinguish between true direction and magnetic direction. Now, intuitively, true feels like the one that matters because that's the map, right?
Correct. True direction is purely geometric. It's based on the spin axis of the Earth. If you could stick a giant pole through the planet from top to bottom, the points where it exits are the true north and true south poles.
The axis of rotation.
The axis of rotation. This is fixed. It is stable, relatively speaking. When we draw a chart, the meridians, those vertical lines of longitude, they all converge at the true poles. So true north is simply the direction along a meridian toward the geographic North Pole.
And in a perfect world, our compasses would just point there. But they don't.
No, they don't. The only instrument that truly finds true north all by itself is an inertial navigation system, or INS.
Okay, so how does that work? Is it GPS?
No, it's even cleverer than that. It uses a set of high-precision gyroscopes and accelerometers to actually sense the rotation of the Earth itself.
It can feel the planet spinning.
In a way, yes. It detects the spin vector. So an INS can align itself with the Earth's axis of rotation. It is technically a true compass, but that is expensive, heavy, complex technology.
Right, not something you find in a Cessna 172.
Not at all. So for the vast majority of general aviation, and even as a critical backup in airliners, we rely on the magnetic compass.
Which brings us to the molten goo problem in the center of the Earth.
The geodynamo, yes. The Earth's core is a chaotic mix of molten iron and nickel. It's thousands of degrees and is constantly churning and flowing.
Like a pot of soup.
A very, very large and very metallic pot of soup. These convection currents act like a massive electrical generator. They create a magnetic field that envelops the planet. Now, the classic textbook analogy is the bar magnet. You imagine a giant red and blue bar magnet buried in the center of the Earth.
It's a clean image, but it's a bit of a lie, isn't it? It feels too simple.
It is a convenient simplification. It's what we call a lie to children. It helps to visualize the basic dipole.
All right. Many thanks for listening to this free part of the ATPL Theory podcast. If you want to continue learning and access the full comprehensive guide, go to my Patreon at patreon.com/ATPLtheory or my Hero at herohero.co/ATPL. That is patreon.com/ATPLtheory or herohero.co/ATPL. Wishing you all the best